Hi everyone. In this video, I want to look at 3 different practice problems where we use free body diagrams to either determine the overall net force acting on the system or to determine unknown quantities of force in given directions. We're going to increase difficulty as we progress through the 3 different questions. For our first question, we'll start off with this scenario shown here. We have an object and it has 2 forces only acting in the vertical direction. We have a force due to gravity of 25 newtons pointed straight down, and we have a tensile force of 40 newtons pointing in the upward direction. A scenario that might describe this free body diagram could be you have a box that is being lifted by a rope. So first thing we need to do is to establish our reference frame for this free body diagram. As I mentioned in class, I recommend using a reference frame where our origin starts at the center of the box, and I usually show the negative y direction directly down and the positive y direction directly up. For this problem, we need to solve for the net force in this vertical direction. So to do so, we need to write our equation for net force. So remember, net force is the sum of all forces acting on a system or an object. So we will have to add these 2 forces together. So we can write our equation, net force equals, and add our 2 forces. We have our tension force plus our force due to gravity. Now here's where we have to be careful because remember, direction matters. The force due to gravity is pointed towards the negative y direction. So we can add the force due to gravity, but we need to make sure to include that negative direction. So essentially what we're doing here is by adding a negative is we're subtracting the force due to gravity from the tension force. Once we have our equation, we can now substitute in the values that are given. We have 40 newtons for our tension force, and we will add a negative 25 newtons for our force due to gravity. You subtract these from one another and you end up with a positive 15 newtons. Now make sure when you report your answer that you include direction with your answer. So it's 15 newtons in the upward direction. For our second problem, things get a little bit more difficult. Now instead of just dealing with forces in a single direction, we have forces in both the vertical and horizontal direction. So we'll need to make sure to only focus on one direction at a time while we solve for our net force for this problem. Like we did last time, let's set up our reference frame. I'll show the vertical axis as the same as last time, the origin at the center of the box, negative y direction directly down, positive y direction directly up. Now for the x direction, again, origin at the center of the box, I will have positive x going to the right and negative x going to the left. All right, so how I recommend tackling a problem like this is to actually split your page into 2 different sides. We will have a vertical and a horizontal. And I'm actually just going to draw a line right down the page. And now we can solve our problem just focusing on one direction at a time. And I'll even take this a step further and redraw the free body diagram, only including the forces in the direction that I care about. So for our vertical direction, I'll show our free body diagram with our force due to gravity and our normal force. And for our horizontal free body diagram, I will only show this frictional force. We have no other forces in the horizontal direction, so our free body diagram only has the one force in the horizontal direction. So let's solve for our net force in the vertical direction. Again, we'll have to write an equation for the net force in the vertical direction. And I'm going to add a subscript v just to represent this vertical direction. Okay, we have our normal force. Remember, we're just adding all forces in the vertical direction. And we have our force due to gravity. But again, force due to gravity, like the last problem, is in the negative direction, so we'll make sure to add the negative sign. Now, if we look at the problem, we see that both the normal force and the force due to gravity is equal to 3 newtons. So we will substitute this in. So what we see by substituting this in and solving for the net force is that the net force is balanced in the vertical direction. We can see that in the case of the normal force and the force due to gravity, they have equal magnitudes but are in opposite direction, so they should be balanced. Mathematically, we can confirm this because anytime we see a net force in a direction of 0 newtons, it means that we are balanced. So our forces are balanced in the y direction, but what about the x direction? Well, we only have the one force, which means that we have to have an unbalanced force in this direction. So we can do the same thing and write our equation for our net force. This time I'm going to use lowercase h for horizontal. And we only have the one force, this frictional force, and it's in the positive direction, so I don't have to worry about my sign. From above, we see that the frictional force is 5 newtons, so we will substitute in 5 newtons, and that is our net force in the horizontal direction. But let's always make sure to include a direction with our vector. So the way I would report the overall net force for the system, because we're balanced in the y direction and we only have a net force in the x direction, is I would say the net force is equal to 5 newtons towards the right. For our final problem, I want to explore how we can solve for unknown forces in given directions when you're giving some of the forces on the free body diagram and the net force. So the first step I take when looking at these sorts of problems is I look at the net force and see what direction that net force is in. So in this case, it's saying the net force is directly to the left, which gives us important information. It says that in the vertical direction, the up-down direction, our forces have to be balanced. So if we're trying to find the magnitudes of force A and force B, we can already determine what force A has to be. Remember, to have a balanced force in a given direction, the forces have to be equal in magnitude and opposite in direction. So we have a force going directly upward that is 300 newtons. That means force A must also be 300 newtons. And it's pointed in the down direction. So now we just have to solve for force B. We're given the net force and we're given the force to the left, which means that now we can solve using the net force equation. So we'll write this up like we did before. We have our force B that we're trying to solve for. Remember, we're adding all the forces together. So like we did last time, we'll have positive x direction to the right, negative x direction to the left. Now, this isn't labeled with any name of force, any type of force. It doesn't say friction or tension or any of that. So I will label this as force left, just to identify on the free body diagram is that force going towards the left. Now we need to also remember that we need to include a negative sign in that because it is going in a negative direction of our reference frame. And so you have two approaches you can take now. You can either rearrange the equation to solve for that B force, or you can substitute in values now and then simplify and rearrange. I like to rearrange the equation first before I start substituting in numbers to make sure that I'm setting the whole problem up to solve for the value I'm interested in. So since I have a negative sign here, we can add this left force on both sides. You add a positive to a negative of the same value, and those will cancel out. So our B force is going to be equal to our net force plus the force to the left. All right, now we need to remember that our net force is actually negative as well. We said our net force is going to the left. So I am going to actually include a negative sign in front of both those forces. And now we can just substitute in and solve for the problem. So our net force, as given, is 60 newtons. So we'll have negative 60 newtons. And our force to the left is 80 newtons. Now remember, because we added the negative left force when we moved it to the other side of the equation, we got rid of that negative sign, right? So it is actually now a positive. So we can simplify this, and we see that our force B is equal to 20 newtons. That's 20 newtons to the right. Now let's do a sanity check and make sure that this makes sense. We're saying our net force overall is to the left. And so what we should expect to see for the B force is a value that is less than this 80 newtons to the left. Because if we're adding the forces and we have a net force going left, that means that this force over here, this 80 newtons, has to be greater than the B force on the right side of the free body diagram. And that's exactly what we see. We see that force B will only be 20 newtons, while the force to the left remains 80 newtons. And that's how you solve these three problems.